process. So that's what we're going to try and talk about this morning. This first couple of hours, and then that'll be followed by a lecture from Nick at probably about 11 o'clock or shortly after on the design strategy. So that's what we're going to try and cover this morning. So, design for assembly, and we're going to use this particular approach called the Dewhurst method. And this is a well-established industry standard approach to thinking about how we can consider the designing a product from an assembly viewpoint at a very early stage in our design process. Okay, let's think about some definitions first of all before we go on. So, design for assembly, or DFA as it's obviously known, is a method of designing a product for ease of assembly. So it's a relative judgment about how easy it is to assemble a product in one way as opposed to adopting some other method of doing it. So what we're looking for is the best possible approach that gives us the easiest approach for assembly. And that ease of assembly is usually determined by the time it takes to assemble it. Obviously, if we can assemble this product in 1 second or less than that, then that's an extremely fast assembly process. Most products are obviously going to take longer than that. And what we're trying to do is to find the optimum set of conditions that give us the right or minimum assembly time for the proper function of our product. So it's a fine balance that we've got to achieve in every product that we're developing. Now I know that some of the groups already are thinking about how we can minimise the number of parts in our product, and of course it stands to reason that if we can minimise the number of parts, we've got a good chance of minimising the assembly time. And the logical extension of that is that if our product could be just one part, then we eliminate all the assembly time. Now that's probably going to be physically impossible to achieve, but you can see the range of possibilities that emerge as we minimise the number of parts. And that's going to simplify whatever process we choose to assemble our product. So, design for assembly, the DFA is effectively a tool to assist design teams to think about how you're going to assemble the product, and importantly, to think about minimising the cost of that assembly, minimising the time of it, minimising the number of parts, and choosing the right approach for your business and for your particular product. So that's what we're going to try and do, or look at. So, in essence, what we're trying to do is to optimise the parts of the system for assembly. We're trying to get our design to be the best it can possibly be for the assembly process that we choose for it. Okay, it's interesting also to contrast that with design for manufacturing. Just discussed design for assembly, but we can also think about design for manufacturing, and perhaps you're more familiar with that terminology, what's involved here. And in that case, we're trying to design for the ease of manufacturing of the collection of parts that make up our product. So we've got to look at each individual component that's part of that assembly to think about how we can simplify the manufacture, and in turn, if we do that, we can simplify the product cost, and we've already looked at what makes up that product cost. So there's a combination of two things here. One where we're trying to think about the overall assembly, because we know we're going to perhaps make millions of these products in a year. So we've got to think about how we're going to do that. But also we've got to think about the individual manufacturing of every component that goes into that assembly. As we'll see, not only have we got to think about how we're going to manufacture it so that it can perform its function in the assembly and how it's going to be used, but also how does it perform its function when it's actually being assembled. And we'll look at some of the difficulties we can have with components if humans are assembling them, or if we've got robotic assembly or some other form of automated assembly. That might change the geometry of the components that we're having to manufacture to make that process easier. So these are some of the things that we've got to consider. But overall, in this particular case, what we're trying to do is to optimize the manufacturing process. With the assembly, we're trying to optimize the assembly process. Here, we're trying to optimize the manufacturing process, or in fact, manufacturing processes. plural. So we've got to keep those two things separate in our minds when we're looking at this whole activity, and make sure that we get the best in both areas. But this morning we're going to concentrate on the design for assembly. So I tried to stress already that it's important to decide at an early stage in the design what type of assembly system we're likely to be able to adopt. What approach are we going to take to actually assemble our components in our system? Now, why is it important to do it early on? Well, because it affects our design. If we say we're going to design it using robots, and it's 100% robotic assembly, that will affect how we design our product. If we decide that we're going to do it 100% manual assembly, that again will affect how we design our product. And those of you who will be going on a visit to a company called OKI will see how they've adopted their assembly processes to suit the design of their product and vice versa. So you'll see that consideration in action on a visit to that particular company. But we have to get that balance right. And as we'll see, that balance is also decided by what our company investment policy is going to be. For example, if we're a very small business, we don't have much capital, and we haven't got much borrowing capacity, then we might have no option but to manually assemble our product, because we simply can't invest in the equipment that's needed. On the other hand, if we are a very large company, then our decision might be very different. We may have money that allows us to invest in new plant, new equipment, and new facilities around the world that might perhaps allow us to fully automate the assembly of our product. So it depends on what your business strategy is going to be, what assembly process you finally adopt. So it has to be decided quite early on. So as I pointed out, it's based on a number of parameters. For example, the production volume is clearly an important one. If we were only going to be able to make one AccuHailer every year, then our assembly process would be a very easy decision, wouldn't it? We'd assemble it manually. There wouldn't be any choice. But if we're trying to produce millions per year, and we're trying to keep the cost down, then the higher the volume, the greater our consideration of some automation of our assembly process, the greater we have to think about that and think how can we bring that to bear in our process. So we've got a number of company parameters, and all of that leads to what our investment policy is going to be. And as we'll see, if we've got a different investment policy, we could end up with a different decision about how we're going to design and assemble our product. Hopefully you can all see the logic in that approach, yeah, even before we know what the detail is. But it's an important consideration, and within your groups, you're going to have to decide what your company's strategy is going to be, what your company or business investment will be. So one group may decide one thing, another group may decide something very different. Now remember, we're trying to design this product for use in developing countries. Now we've got a decision in each group. We might decide that what we want to do is to have the assembly and the manufacture actually in the country in which we're selling the product. If we make that decision, then we've got to think about what the investment policy would be in that environment. On the other hand, you might decide that you're a big international company, big drugs manufacturing company, and you're going to do all the manufacturing in the middle of New York. If you're crazy, you might decide to do that. Yeah. Again, your decision and your investment policy is going to be very different if you make that decision about where you're going to manufacture it and then ship it around the world. The two things are very different. And I want each group to think about what they would do if they were in that situation. What would you do? And so that will mean that each group will take slightly different approaches to how they're going to design and manufacture and assemble their particular product. And that's what I want to see coming out of all the groups that we're dealing with. So that's the basic approach that we're going to think, or you're going to have to think about. We've also got to remember that the cost of assembling a product is is, as I have suggested, related to both the design of the product and the assembly system that we're using. Both of these things will come together. And those of you who are doing the costing, who've taken on that responsibility, have to recognise this and have to take this into account. What is our cost of assembly for our particular product, given what we have decided, and what is the cost of manufacture at the same time? So there we've got to get that balance right. And of course the lowest cost can be achieved by designing the product so that it can be economically assembled by the most appropriate assembly system. You have to design the product, if you're going for assembly, so that someone can actually physically pick up this component and accurately locate it within the device. If they can do that within a certain amount of time. You have to design the component so that can happen. It doesn't happen by accident. It happens because you, the designer, have made it so. You've got to think about every component in that way. So deciding what system we're going to use is important very early on in our design process. Okay, you're probably aware of this, but it's worth reiterating that the methods of assembly basically fall into three different categories. The obvious one, manual assembly, but then we move into increasing automation. We might have some form of special purpose machine assembly, machines that have been specifically designed to do a particular task, or we may go to an extreme where we've got fully programmable machine assembly, fully robotic, no people involved at all in that assembly process. Now deciding on which one of these we go for has a large bearing on how we design the product. Now I'm talking about the detailed design of the product, not the overall functioning of it, but the detailed design of how it all goes together. That's going to be controlled to a large extent by which of these approaches we end up adopting. And we have to have a logical basis on which we make that decision. We can further subdivide this into these categories, and these codes that you can see at the side here, MA, MM, AI and so on, these are just the codes that the Boudroyd Dewhurst approach adopts to designate each assembly approach. So it can go from MA, which is totally manual assembly utilising some kind of transfer device and work carriers, to MM, where we've got manual assembly utilising single purpose part feeders. So each code tries to define each approach to the assembly that we take. Now if, for example, we adopted, say, MM as our approach, then what we're saying is that we're going to utilise part feeders. So we're already saying that we've got some kind of system that holds the components and then delivers them to the manually assembly worker. So they have to be delivered in the right format, in the right orientation, so that the person can pick up the part and put it into the assembly in the correct way every time. So you have to think about what happens to the component when it's in that hopper system before it delivers it to the manual assembly operator. Could the parts jam together? Could they be damaged physically because they're all in this vibrating hopper that's delivering the parts to the worker? You have to think about that. You have to think about what could happen in that situation, and have you designed the component correctly so that there's no interruption to that assembly process. So suddenly you're going to start thinking that there's a lot more to designing a component than perhaps you previously thought. You thought it was just about making it so it didn't break during performance, or that it could be injection molded. But I'm going to suggest to you today that you have to design it so that it can actually survive the assembly process. So it's not going to be damaged during that process or weakened before it finally finds its way into the full product. We've got to design the product for that complete process. And hopefully now you're beginning to dawn on you, this is why it's important to work in a group and to share the different expertise that each member of the group is now going to acquire. Because the person who looks into the assembly area has to be able to communicate with the people who are thinking about the manufacture of the product, who are thinking about the injection molding of it. How do we alter the geometry so that it's ideal for that complete experience from its manufacture right through assembly and into use. We've got to think about the complete process. Okay, so these are the subdivisions that we might consider, and this is a way of graphically representing each of these different techniques. And you can see along the end here, we've got manual assembly, then we've got a special purpose unit, and that might be that we have various stations and the components of the parts circulate around these stations, or we may have an inline assembly process, or we may go to robotic assembly and have different cells to help us in that manufacture. Each one of these approaches demands a different detailed design of our product. Yeah. They might look the same externally, but they might be very different at the detail level of the components to make them suitable for each of these processes. Now, one thing every business has got to think about is what happens if our business changes over time. So, for example, let's imagine we start out our business, we haven't got much money, so we start with manual assembly. And we've got a very basic assembly line. But let's imagine millions of people start buying our AccuHailer, and we start making a lot of money. We get past our break-even point very quickly, we're into profit very rapidly, and we start making a lot of money for ourselves and our business. And the growth, the demand starts to increase. What do we do? Well, let's imagine that happened. We're here originally manufacturing this way, but once we get money, how can we shift to a much more efficient manufacturing and assembly process? If we haven't designed our components carefully, then it might be that shifting to this process becomes almost impossible to do. Yeah, because we haven't got the components designed in such a way that they can take advantage of this environment. And many companies do this. They end up trying to switch from the manual to the fully automated using the same component design. And what they find is that this process here starts to become costly because the components aren't optimized for that manufacturing process. And often it's too late then. You have to think, okay, how can we change our design to optimize it for this process? By such times, they've started to lose money, they've become inefficient, and their business starts to suffer. The really clever business, if they can look ahead and see how they might develop, they are maybe operating here, but they're immediately thinking, how would our components have to change to make it suitable for this process? Or, if we're really, really clever, can we think about how to design it so that the components will automatically be suitable for this process? Can we achieve both things in one design? That's the sort of thinking, the joined up thinking, that you've got to bring to your design in your groups. So, let's move on. Let's look at an example to try and see how we might begin to think about this. So let's imagine we've got an assembly of a product or a system, and it consists of 35 parts in the total assembly, and we're trying to assemble this at an annual production rate of 500,000 per shift, with 2 shifts being work per day. Does everybody understand what I mean by a shift? A shift is a normal 8-hour working day in a business. Yeah. So someone may work from, say, 8 o'clock in the morning till whatever time later in the day, 8 hours later. Then they might be replaced by someone who works throughout the night. Yeah. Or there may even be someone who then comes on and works from the late at night to early morning, if you're working 3 shifts per day. So it would be 3 8-hour shifts. So we've got to think about that. What is our working strategy going to be? For this business, they're saying they're going to work 2 shifts a day. So they may have a normal shift and an evening shift, or whatever. The company also has a policy to say that the amount to be spent on an item of automated equipment that will do the work of one operator on one shift is twice the total annual cost of employing one assembly operator. So what they're saying in that is that if we can replace a person working with some piece of equipment, then we're prepared to invest twice the cost of actually the amount that we annually have to pay to employ that person. Only if we can replace them with a piece of equipment. Now that's feels a cruel decision, doesn't it? Because somebody's going to lose their job and be replaced by a piece of machinery that can do their particular job. But that's the kind of hard decision that manufacturers and businesses have to make. You have to decide how much are we prepared to invest to get to this fully automated, fully optimized environment. And that's a very difficult decision for businesses to make, especially if it's people who have been working there for a long period of time. But that's the reality of businesses that have to make a profit. Right? So you and your groups have to think of yourselves a bit like a business and say, what are we going to do? What's going to be the right thing for our business and for the strategy that we adopt? So we're asking you in this few weeks to really take a rather mature view of how we design and develop a real product and what the impact is of what our decisions are during that process. Okay, so we've got the idea of what our business is trying to do here. So from that we can develop what we call an investment factor. So here it is, it's called RI. Again, it's just the code that Boudreau and Dewhurst use. But you can see how this equation is developed. First of all, we've got SH, which is the number of shifts that we're working. It's either 1, 2, or 3. QE, which is our capital equivalent to replace one assembly worker. Now, in the scenario that we've painted here, we've said we're going to invest twice their annual salary. Another company might decide something else. They might decide it's worth paying 3 times that, or 4 times, or even 10 times, whatever it is, for their particular business. But for this particular one, this is what the strategy is for this particular company. And then of course we also have to know what the annual cost of employing one operator is going to be. So we can multiply the number of shifts times the capital equivalent of replacing one operator divided by the annual cost for employing that person. So that gives us our investment factor that we're going to use in this particular situation. And that will vary, as I've tried to stress, from one company to another, or in your case, from one group to another. You have to decide what your investment factor is. You have to be able to justify it. It has to make logical sense, given the scenario that you're working in. So please, those who are looking at these factors, think about that. Okay, so in this example, if we put the numbers into our equation, we get an investment factor of 4, because we're letting our annual salary going to be £20,000. Again, that annual salary is going to vary, depending on where in the world we're employing people. Yeah? It might be 20,000 in the UK. It might be very different if we're employing people in Brazil, the Philippines, or Singapore, or wherever we're employing them. It will vary. And as a business, we've got to think about that. Because if we're employing people in a low wage economy, then it might be easier for us to make that to make that investment in automated equipment, because our wage costs are so low. So we have to decide what is the right approach for our particular business. But in this particular case, we've got an investment factor of 4 that we're going to work with. There's some other factors, though, we have to take into account in our business, and I've listed some of them here. And so these are other parameters that are going to affect our choice of assembly. Things that are very practical in nature, and we've got as a business to think about it. The first one, perhaps, is the most important. What is our anticipated production quantity going to be? Now, in this case, we've said 500,000 per annum per shift. So if we work just 8 hours a day for a whole year, we would want to produce 500,000 of these products. In this particular case, is that sufficient to meet the demand? It may be. It meets the demand for your particular product. Maybe it doesn't. Maybe it's not sufficient. In which case, you would have to reconsider that. But you've got to decide in your business what that production quantity is likely to be. And this is where consideration of your design specification becomes real. So when you were maybe thinking about product design specification in your first semester or last semester in Singapore, and you're trying to decide what a production quantity is, it probably didn't mean a lot to you. It's just a number that you had to put in that design specification. What I'm saying to you now is that it has extreme importance, because you have to know what that target is likely to be. If that value was 50,000 rather than 500,000, you'd make a very different decision about how you're going to assemble this product and how you're going to manufacture and detail the components within it. Equally, if this number became 5 million, again that's going to change how you're going to make and develop and invest in this particular product. So that number that you come up with in your design specification is crucial. You have to give it serious consideration before you embark on your design process. Other things we've got to think about is the number of parts in our assembly, and here sometimes we have to make a rough estimate. We can look at, for example, the existing AccuHailer, and we can work out how many components in that, because we can take it apart and check it. But we also have to say, how many components are we likely to have in our proposed design? And we have to make that judgment before we know exactly what the final design might be. So all the time we're trying to say this is likely to be the outcome, but refine that process as we go through it. Other things we have to consider, and this is perhaps quite an unusual one. What are the number of design changes anticipated in the following year? As you probably know, no product remains fixed forever. It would be nice if it did. But there's always something goes wrong, or something that we have to improve, and the design changes slightly. How can we anticipate what these design changes might be? And how many changes can we expect? Because if we find halfway through assembling our product in a particular way that something has to change, because say it keeps failing when people are using it, if we find that has to change, then that could have an important impact on our whole assembly process. We might find that the equipment that we have built and designed to help that assembly no longer work efficiently because of this design change. So we either have to think about scrapping all that equipment and getting new equipment in. What do we do? So anticipating these likely design changes is important. And this company will say we're thinking about that it's almost non-existent, the number of changes. The number of parts required in the model range. Now, what this refers to is to imagine we're a company and we're making an AccuHailer, we're also making some other kind of medical device, and then we've got maybe a third product. And we're producing all these in our factory, set on separate production lines. But they share some components. That's often the case, particularly if you look at the automotive industry. If you're looking at BMW, for example, they may have different lines for the Series 7, Series 5, whatever, being manufactured, but they might share the same windows, or they might share the same engine in some cases, or they might share the same seats. So they're sharing components across 3 different product ranges. And that could happen in something like the AccuHailer as well. You could have similar components being used across a range. And that would be a very sensible approach in a manufacturing environment, because then you're getting the full economic benefit of high production of individual components and sharing them across a product range. So that's something we have to think about, what's going to happen. And then, of course, we have to think about the product life without significant variation in demand. So this last point is linked to the first point. For how long do we think we're going to have this demand on our product? And your business has to try and forecast what that demand is going to be. Because if they get that wrong, and you suddenly find the demand changes from 500,000 per year to 5 million per year, then your production line might be completely out of date, inefficient. You may have to start building new factories, doing whatever it takes to meet that demand. If you don't, other businesses will pick up that work and start making profit that you're losing. So all these things have to be considered. Now they're very difficult often to be precise. Yeah? You're going to find that you can't be exact about this. But your business has to say, what's our best estimate? And what are we prepared to take a risk on in this particular case? It has to be done. Okay. Now, we've got a chart here, and you'll be able to look at these charts in the notes in some detail. But what this does is try to bring together all this consideration that we've just been thinking about. The idea of how many parts we're going to have in the assembly, what's our investment factor, and that's shown here. There's a range of different investment factor numbers that we could consider. We also have to think about our production volumes per shift, and they're given down the y-axis, if you like, on this table here. So when we look at all the various parameters and work our way down through this chart, we find that everything coincides here, where it says AP. So we've got our investment factor, we've got our production volume per shift. This is telling us that, given the experience of other businesses in many different areas, that it's saying that AP, in this case, is the preferred approach to the assembly process for this particular product and for this company. And let's just remind ourselves what AP is. There it's there. So this is the kind of assembly environment that we're saying that this company should adopt, or that the Boudreau-Dewhurst method is suggesting is right for that company. So here we are, we've got some automated equipment. It might be robotic arms that are helping us in this process. We've got some kind of carrier system to transfer the products along this system, and these automated pieces of equipment do some work in that process. And again, the people who go to OKI are going to see something like this process in operation. And you'll see when you see their product why they've adopted that particular technique. So that'll be useful to make that comparison between what you're doing and what that company does. Now you might find when you go through this process that you choose some other assembly process. It depends on what you choose by going through that selection chart. Now that selection chart, as I've stressed, is based on past experience. Experience of many companies, on what their investment factor policy has been, what their production volumes have been, and end up what assembly process they have ended up adopting for their particular product. The Boudreau-Dewhurst approach gives you the benefit of that experience and the ability, to think about what that process should be for your business at the very earliest stages of developing your product. So after today, what I'm hoping is that each group will be able to go along, think about their product, bit of discussion within the groups to say, what are the basic parameters that we're basing our design on? And therefore, which assembly process does it look like we should be adopting for our particular product? And our assumption of where in the world we're going to manufacture and assemble this product. Okay, so that's the basic approach for that. But on top of it, we can also start to think about something called design efficiency. And Boudreau-Dewhurst give us the methodology to allow us to start thinking about how efficient our design is going to be. So once we've got our appropriate assembly method decided, then the next step is to think about, well, how efficient is our product to make use of that particular process? Yep, we've already been given an indication that it's okay, it's in the right direction, but how efficient can we make our product now to effectively optimize it for that particular process? And And there are two important stages in this. You can see those in the bullet points at the bottom here. We need a decision as to whether the part or parts in our assembly can be eliminated or can they be combined with other parts in the assembly. What we're trying to do there is to reduce the number of parts further. So we may have designed it with our first best guess on how we should make this part for a particular assembly method, but now we're trying to refine it, we're trying to optimize it. So we get to the point of saying, can we combine one or more parts together to further simplify the assembly? Now there's an important point here, that combining parts together to simplify the assembly might lead to making it more complicated to manufacture. And so when that happens, we've got a balance, yeah, that we have to decide what's the best thing to do here. Increase the complication in the geometry, which makes it perhaps more expensive to injection mold, or do we accept that complication in the geometry to make it easier to assemble and quicker to assemble? What's the right decision? Only you and your groups can make that decision based on what your investment policy is and based on the cost structures that you've got for your particular product. That's why it's going to be important when you come to presenting your ideas to be able to justify how you've come up with your final product. Where have you decided to incur the cost and to accept slightly lower efficiency in assembly to make it cheaper to manufacture? So the people who are doing this costing have got to be able to justify that and show how they've decided on that balance. Give that considerable thought. The next important point is an estimation of the time taken to grasp, manipulate and insert the part in the assembly. Once we estimate that time, we can then ask ourselves, how can we change the component so it's easier to handle? Yeah, and reduce that time further. Or how easy is it to manipulate it into the position in the assembly? Yeah? How can we make that more efficient? And how can we do it again without jeopardising the benefits that we've maybe got in terms of our manufacture of the individual components? So there's a conflict here going on sometimes about how easy it is to assemble compared to how easy it is to manufacture. And what your job is to get the right balance between those things. Okay. So once this information again is available, once we've got what our total assembly time is, we can compare it with a theoretical ideal design. And this is the approach that Boudreau and Juhas take. They say there's a theoretical ideal that maybe you're never actually going to be able to achieve, but you should be trying to head in that direction. And you can compare your design that you've got currently with that ideal. Okay, so how do we do that? Once we've got our position, how do we determine that ideal? Well, this ideal assumes something, and assumes that each component can be assembled in 3 seconds or less. Yeah, each component assembled in 3 seconds or less. And that's from the time it takes to pick up the part, get it in the right orientation, put it in the assembly. When you were looking at your assembly on Thursday, if you had taken the time to think about how long it took you to do each task, then you would get some estimate, or reasonable estimate, of what your assembly time was going to be. Yeah? That's worth doing again next Thursday. The person who's responsible for this should maybe time how long it takes to put each component in that assembly, so that you've got a reference point to say, to manual assembly, we estimate that this product takes this length of time, and therefore our design is more efficient than making that particular product. So be ready next Thursday, the people who have already accepted this task, to take that product apart again and to check how long it takes to assemble it, and to record how long it takes to assemble it. Okay, so if we do that, we've got a measure of our design efficiency. So this number here, 3, is our 3 seconds. Yep. NM is our theoretical minimum number of parts. By that we're saying, what is it, do we think the absolute minimum number of parts is going to be in the assembly of our design idea? And then TM is our total estimated assembly time. So you can see here that this efficiency is 3 seconds times each component, the minimum of which we've considered, and TM is our total estimated assembly time. What do we estimate that total time is going to be? And from that, we've got a comparison between our design and a theoretical ideal. And that gives us our indication of what our design efficiency is going to be. That's all very well. Let's look at an example of this in action. Here we've got a design of assembly for a particular latch mechanism. I think it was used on a photocopy machine. And what we're doing here is looking at this design to say, how can we benefit or improve it from thinking about this design for assembly evaluation? Let's consider this product. And I'm going to use the Boudreau-Durst approach to think about this. Now this is the existing latch mechanism that the designers had come up with. Now you've got no way of knowing if that's a good design, a bad design, whatever. Yep, it's just a design of a particular latch mechanism. But you can tell by looking at it that it's made up of a number of parts, quite a considerable number of parts. Now maybe they're all necessary, maybe they're all essential, maybe they're all optimised from a point of view of manufacture, or maybe, just maybe, there's a way of improving this design, of making it more efficient, of combining more than one component together to think about how you can improve the assembly time whilst avoiding making the manufacture too expensive or too difficult. So that's what the kind of situation you might be forced with thinking about. But we need a starting point. We need the starting point of your concept. What's your idea about what your design should be? And then let's see how we can refine it, how we can optimise it from a manufacture and assembly point of view. Okay, so let's imagine for this particular example, this is the information or the approach that this particular company is taking. We've got, it's quite expensive to employ someone in this particular business. We're only working one shift. The cost of employing one operator is 25,000, so we're prepared to invest 50,000 to replace that person. So our investment factor here is going to be 2, using the formula for the investment factor that we saw earlier. We've also got some other parameters here. We've got an anticipated production quantity per shift of 10,000. We've got 62 parts in our assembly, and we've made some estimate of how much change we're likely to have in this particular design. So that's our strategy for this particular business. You need to try and complete this for your group. Yeah? We expect to see this kind of table in the report of the person who's looking at this particular aspect of it. And it has to be decided by the complete group. So we look up our Boudreau-Durst chart. We go through our various considerations, find our investment factor, find our production quantity, and we can see that at the bottom here, this is where we converge in this particular case at NM. So this is telling us that with that investment factor, with that particular product, with the quantity we're producing, we're going to have to manually assemble this particular product. Now that might not have been your initial thoughts when you first saw this particular product. You might be thinking, oh, that's complicated, maybe we should automatically assemble this. But what I'm trying to get across to you here is that we need to have a strategy. We need to know what our business strategy is going to be. We need to know what our business is going to try and achieve and what the market is going to try and do before we can make that decision. And it's dangerous to make that decision otherwise. Yeah? You need to think about what your business wants to do, how the market is likely to develop, and you've got to make the best judgment you can to try and meet that demand. So that's why we need this company-specific data. And And it helps us then to choose and to target what we're going to do here. But of course, once we've chosen that, we've got to look at our design and say, how can we make it better? How can we refine it and optimize it for that particular approach? And this is one attempt to try and do that. So the designers have said, okay, we're going to try and manually assemble this. How can we make it, optimize it so that it can be done in that way? So you can see here that they've combined some components, and it might be that that component there, which is a combination of more than one of the previous parts, might be a bit more expensive to make and manufacture, but it might save a lot of time and a lot of effort and make things a lot easier to manually assemble. Yeah? So you see the approach that you've got to take here. So you've got to think about how we get the right optimized components for our assembly and also our manufacture. And the Boothroyd-Jones approach tries to drive you in that direction. It's trying to make you improve the design efficiency of your product to get it the best you can possibly make it. And this approach shows that approach in action. So here's a summary of the comparison of the two. So we've got the manual assembly efficiency when you work it out. The old design was only 7.2% efficient. Well, I guess that's obvious now when you see the number of components. The new designs push that up to 34%. Significant improvement. The number of parts was reduced from 62 to 17. It's got to be an improvement. As long as the manufacturing cost of individual components hasn't gone through the roof. Yeah, it's a balance in these things. We've identified the theoretical minimum number of parts as being 10, so we could take it further, but we can't quite get there at the moment. We've got our estimated assembly time, estimated assembly cost, the estimated parts cost, and then our total product cost. So it's reduced with our new design from the old design. In fact, we've got a percentage saving here of 32% by changing that design. Now that doesn't happen by accident. It happens by the group being forced to think about how they can improve this design. Now what you're going to find is when it comes to thinking about this, there are going to be people in your group who are going to resist that change. And they're going to resist it because the design that you want to change was their design. And they're going to be very protective of it. Yeah? And they're going to argue that their design is the best it can possibly be. Your group has got to be mature. You've got to look at that and judge for yourself as a group, is that indeed the best or near optimum solution for our design? Because if you get that wrong, and when we come to look at it and we judge differently, you're going to lose marks. So don't be tempted in your group to be bullied by one individual who maybe came up with the idea or thinks they came up with the idea and they want to be super protective of it and don't want anybody else to criticise it. Everybody has got to make a view and the group have got to decide what's the right way forward. How do we change this and can we justify it to Dr. Green and the others when we come to give our presentation? Can we justify that design? What we can't do is stand up there and say, this student designed it, we thought it was good, that's why we went for this idea. That will be insufficient. You've got to be able to justify it. Show that you've tried to improve that design to make it more efficient. Okay? We need to see a chart like this that shows that what you're proposing has improved from your initial design to your final design that you submit to us. Now there's going to be a number of things that are going to help you in that process, some of which some groups have already thought about. The prototypes, the models you make. As soon as you make a model of your idea that you've drawn or sketched, you're immediately going to recognise that there are some things within it that can be made better. Once you make your prototype, again you'll find there are some things that you haven't optimised and that you can make better. Now it's critical that each group shows that they've improved their design based on the knowledge that they've gained from making these models. There has to be that connection. If you recognise that something not ideal, show me that you've improved your design. Make that connection all the way through. So this is just to show you how we worked out some of the details. I won't go through that just now. You can look at that in your leisure. But it shows you how you can begin to think about trying to get this optimised approach, to try and get the best manufacture possible, along with the best assembly possible. And that's what you're trying to drive to achieve. Okay, I think we'll take a break there, and then we'll go through this little exercise just to show this happening with our previous student project. Are there any questions just at the moment? I know one or two people trying desperately to stay awake and some failing at the back there. Couldn't start with my laser.